最后一堂课啦，大家是不是很开心？你别说，我更开心。你们有第17周考试的吗？18周，17最迟17。所以下个礼拜考多少门？都是下个礼拜，除了一门在第17周。所以有多少门呢？下个礼拜考多少门课？4个 ，yes， 开心，加油。今天教的还是很重要，还是会出现在下个礼拜，还是会再见到。对，那个。All right, let's get started with today's lecture, which is about PID control. So, who here has heard the name PID control? Anyone? 有人听过 PID control 是什么吗？没有。你在无人机载具听过是吧？ All right, so in today's lecture, we'll learn about what PID control is. Okay. So this lecture investigates a specific control structure that is quite universally used in industrial control. It is based on a particular fixed structure controller family known as the PID controller family. Now, these controllers have shown to be very robust against uncertainty and extremely beneficial in the control of many important industrial applications. So PID stands for proportional, integral, and derivative. So P stands for proportional, I integral, and D derivative. We'll see why this is named as such later on the next few slides. But for now, you should know that PID stands for proportional, integral, and derivative. So many early feedback control devices in the 19th and the 20th centuries implicitly or explicitly used the ideas of PID, the action, in their structures. But it was not until 1922 that rigorous theoretical consideration was given to PID control by Minovsky's work on ship steering. So the reference is provided here if you're interested in giving it a read. So in this paper, the first mathematical treatment of this type of control, known as PID controller, was covered. And now it is widely used in a lot of industrial processes. Okay. So again, in spite of the fact that there is an abundant, sophisticated control tools and controllers available that have been developed over the past decades, including advanced controllers such as optimal control, robust control, and model predictive control, etc., etc. The PID controller, proportional integral derivative controller, is still the most widely used in modern industry. It is claimed that more than 95% of closed-loop industrial processes are being controlled by PID controllers. So it is an extremely important control structure that you guys should be familiar with. But this references, they're dated, in the years 1995 and 1991. So the percentage here might not be as accurate as now, because now there could be more artificial intelligence or model predictive controllers that are being used for controlling industrial processes. But still, PID controller is universally used and widely important in the industry. Okay, so let's now look at the structure of a PID controller, having seen the motivation behind studying a PID controller. So ideally, a PID controller takes this form. It is the sum of three terms, the first being a constant Kp, and the second being another constant Ki times 1 over S, and the third term is Kd, a third constant times S. Now, you should be able to immediately see that the first term corresponds to a proportional control, the second term corresponds to an integral action weighted by Ki, and the third term corresponds to a derivative action weighted by Kd. And hence the name PID, right? So 1 over S is an integrator. Multiplication by 1 over S is an integrator. Multiplication by S corresponds to derivative in the time domain. So this is PID controller. We can also factor out Kp. And what's left inside is then a sum of, again, three terms, 1 over Tis, and Td times S. So in this case, Kp over Ti would be equal to Ki, and Kp times Td will be equal to Kd. This is just an alternative way of representing the same controller. In the time domain, if we again consider the input to a PID controller to be E, the error signal, and the output of the PID controller to be U, the control action, then taking the inverse Laplace transform, we get U of t, U as a function of time, is equal to Kp times E of t, the error signal, as a function of time, plus Ki times the integral from initial time, which is taken to be 0 usually, and you integrate up to time t, the error signal, where theta here is the dummy variable of your integration, plus Kd times the derivative of the error signal as a function of time. Okay, so again, we see that this is a proportional controller, this is an integral action, and this is a derivative action. And hence, the name proportional integral derivative control can be understood intuitively from this equation here. Make sense? Any question? No? One thing to note here is that the structure stated on the previous slide is improper. What does that mean? So when a transfer function is improper, it cannot be physically realized. We talked about it in one of the previous lectures, right? So why is this an improper transfer function? Anybody? Do you still remember the definition of properness of a rational transfer function? What does it mean for a rational transfer function to be proper? You shrug your shoulders and then yeah. What does it mean for a rational transfer function to be proper? What's the definition of properness? Yeah? Yes? Perfect. So the degree of the polynomial in the denominator should be no smaller than the degree of the polynomial in the numerator. Right? That's when a transfer function is proper. So is this the case here? What is the degree of the polynomial in the denominator for this PID controller? And what is the degree of the polynomial of the numerator? Any idea apart from this student here? 那它分母的多项式的那个叫什么？是这个有的 degree 是多少？然后分子是多少？It looked like this, right? A PID controller. So this is a rational transfer function. It's one polynomial divided by another polynomial. So what's the degree of the polynomial in the numerator? That's 2. And what's the degree of the polynomial in the denominator? That's 1. Exactly. So 2 is greater than 1. So this is an improper transfer function. It's not proper. So what does that mean physically when a transfer function is not proper? It means you would have some derivative action. It means here the multiplication by s will be present. So I believe I've explained in one of the previous lectures that when you have multiplication by s, which corresponds to a derivative action in the time domain, this is not physically realizable. It's not physically implementable. You cannot physically realize it, such a controller. Why? Well, because this guy would have an infinite gain at high frequencies, right? So the gain of multiplication by s increases as the frequency increases. So there's just no such device in the world, in the universe, that you can use to realize a derivative action. Right? And also, if you remember, taking the derivative means that you have to approach. So at one point, at one time instant, when you take derivative at one time instant, you have to take the limit from the left and from the right. So you're taking the limit from the left, that's okay. You're just exploiting information about the past. But if you take the limit from the right, you need information about the future. So imagine a function of time. So this is time 0, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Suppose you want to take the derivative at time 5, okay? Then you need to take the limit from the left, which means you exploit information from 4.9, 4.94, 4.95, 4.99, and that's okay. But then at time equals to 5, if you want to take the limit from the right, then you need information of the function at time 5.001, for example. So then you are exploiting information about the future, which means this is not the causal system. You can't know what your input is at time 5. So at time t equals to 5, you wouldn't know what your input is at time equals to 5.1, 5.01, because that would be knowing the future. Right? So this wouldn't be a causal system. So I've just given you two intuitive explanations as to why an improper transfer function is not realizable. Any question? This is physical intuition that I'm providing you with. 有问题吗? Okay, so this first point, the first bullet point here on this slide says that the structure given on the previous slide is improper, and so such a structure cannot be physically realized, as I just said. So in reality, when we try to realize a PID controller, we would introduce extra poles in the control structure. So to be able to physically realize a PID controller, what we would use instead is this form here, which is Kp plus Ki times 1 over S plus tau I, where tau I is a positive constant that is very close to 0, plus Kd times S over tau d S plus 1, where tau d again is a positive constant that is very close to 0. So it's much smaller than 1. So you can see here that the integrator term, which is the second term here, behaves like a first order low pass filter with a real pole that is very close to the origin. So this is almost like an integrator because tau I is very small. It almost behaves like 1 over S. But to make it, usually what we desire of a controller is stability. So we like your controller to be stable as well. 1 over S is not stable, so we make it stable by placing, or by shifting the pole from the origin to the left a bit. Now we have just shifted the pole of the integrator from 0 to minus tau I, where tau I is a very small number. This makes this part stable, open loop stable. Also here, for the differentiating part, the differentiator behaves like a first order high pass filter with a real pole that is sufficiently far away from the origin. So now because tau d is a very small number, so the denominator is almost equal to 0, it's almost equal to 1. So this term then behaves like multiplication by S. So this is almost equal to S when tau d is very small, right? But what this does is that it makes, so the introduction of the denominator, or a very fast pole to the derivative, is that it makes it behave almost like a differentiator, but it's a rational transfer function. So the introduction of the denominator here makes this a rational transfer function, a proper transfer function, so that it is realizable. you can see that the degree in the denominator is now 1, whereas the degree in the numerator is also 1. So this part becomes realizable, but it almost behaves like a differentiator because tau d is very small. Any questions? So when we're performing PID control synthesis, we usually only consider the ideal scenario. The slow pole for the integrator, this guy here, and the fast pole for the differentiator, this bit here, are added later at the implementation stage. So when we're doing design, we just adopt the ideal form of a PID controller. So when we're designing a PID controller, we just use this form. But when we try to implement the PID controller physically, we add a slow pole to the integrator and a fast pole to the differentiator for implementability, for realizability. Okay. Make sense? Any questions? So now let's look at the frequency domain properties of a PID compensator, a PID controller. So again, we have restated the form, the ideal form of a PID controller up here in the first line. And that's equal to this bit here. Typically, all the parameters Kp, Ti, and Td are positive, positive constants. We can see that the zeros of the PID compensator are exactly the solutions to the quadratic equation in S. Okay, so you can apply the quadratic formulas to find the roots of this quadratic equation, and they're equal to this bit here. Okay. So based on this formula, we can immediately see that the two zeros of the PID controller are real if and only if Ti is no smaller than 4 Td. That means whatever that's inside here is non-negative. Okay. So if this were to be negative, then taking the square roots will give rise to non-zero imaginary parts, right? So when Ti is greater than or equal to 4 Td, the bit inside the square root would be real and positive, and hence we will have two real roots for this equation here, and there are exactly the zeros of the PID controller. Okay? When the two zeros are real, we can define what's known as the central frequency omega naught of the PID controller to be 1 over square root of Ti times Td. And so what is this? Well, let's see its explanation on the next slide. So we can substitute omega naught into the expression, the mathematical expression for omega naught into CPID. We can evaluate CPID at j omega naught, where omega naught is equal to 1 over square root of Ti times Td. And what is that equal to? Is equal to this expression here, which is Kp times this guy here, just by substituting omega equals to 1 over square root of ti times td into the mathematical expression on the previous slide. Okay, and now you can see that this guy is 1, so 1 minus 1 is 0, and this cancels out with this, and so the whole thing becomes 1 times kp, which is just kp. So at omega equals to 1 over square root of ti times td, the central frequency, what we have is that is just a constant. So the attenuation and phase displacement due to the PID controller at omega naught are given by so the attenuation is given by kp and the phase displacement is 0. And hence, at omega naught, the PID compensator attenuates the magnitude of the system by a factor of kp, and the phase contribution is 0 at the central frequency, omega naught. Okay. So, any questions regarding the central frequency or the zeros of a PID controller, or the realness of the zeros of a PID controller? No? Okay, so let's now look at a typical Bode plot of a PID compensator. So what's shown on this slide is an illustration of a typical Bode plot of the PID compensator. In this example, Kp is taken to be 5, Ti 10, and Td 1, in which case the central frequency is omega naught equals to 1 over root 10. Okay, so at the central frequency 1 over root 10, we would have 0 phase contribution. So 1 over root 10 is about here. And this would give us 0 phase contribution or 0 phase displacement. And this number here would be a real constant. We can see that the phase of a PID controller lies between minus 90 degrees and 90 degrees because you have at most 1 pole and 1 0, right? And no, sorry, you have at most 1 pole and 2 zeros. So 1 pole gives you a minus 90 degrees of phase shift, and 2 zeros bring it back to 90. So 1 pole and 2 zeros. Oh yeah, I'll say something about the exam later, but Bode plot is extremely important. So the ability to read Bode plots will be extremely important next week for you. Yeah. Also, because you have an ideal integrator in a PID controller, in an ideal PID controller, you can see that as S approaches 0, the game blows up and it decreases at the rate of 20 dB per decade along the low frequencies. And because of the presence of a differentiator, which is S, you have at high gains, you have at high frequencies the gain of the PID controller blowing up due to the presence of S. Okay. So this increases at the rate of, again, 20 dB per decade, right? So this part is due to 1 over S, this part is due to S. So here, what we're showing here is 2 types of PID compensators. The blue curve corresponds to an ideal PID controller, while the green part corresponds to a real PID controller, a physically realizable PID controller, with the addition of a slow pole and a fast pole. So the green curve corresponds to a physically realizable PID controller, whereas the blue curve corresponds to an ideal PID controller. Okay. So what has happened here? Well, at mid-range frequencies, nothing has changed much. But at very low frequencies, the integrator has become stable because of the introduction of a slow pole, right? So this wouldn't blow up to infinity anymore. And also at high frequencies, because of the introduction of a very fast pole to the differentiator, this wouldn't blow up to infinity. But in mid-frequency range, in middle frequency range, they behave roughly the same. Okay. So that's the difference between an ideal PID controller and a real PID controller that is physically realizable. Okay. Are there any questions? Well, if there's no question, let's take a 10-minute break, toilet break, and we'll be back later. All right. So we have seen here a body plot of an ideal PID controller together with a body plot of a realizable PID controller. So this is the case where we have Kp equals to 5, Ti equals to 10, and Td equals to 1. So in this case, I believe Ti is larger than 4 Td. Is that right? Ti is larger than 4. But Ti is equal to 10, Td is equal to 1. So Ti is larger than 4 Td. So we have two distinct real poles for this example. So what about the case where Ti is less than 4 Td, in which case we have complex zeros in the PID controller. So here is an example, body plot of a PID compensator with two complex zeros. There's not too much difference between this and what's seen on the previous slide, apart from the fact that now the twisting here at zeros is a lot sharper because the zeros coincide at this frequency. So it's not much difference between this plot and previous plot. But here, because there are two complex zeros at the same frequencies, the twisting is more rapid around this corner. Okay? So let's now move on to synthesis. So how do we design a PID compensator? How do we synthesize a PID compensator? So the compensation method presented in this lecture is based on the design of a compensator such that the phase margin and the crossover frequency omega naught are specified. So we specify what the phase margin and the crossover frequencies we want our closed loop systems to have when we design the PID controller. So this design method presented in this lecture is based on the knowledge about specified values of the phase margin and crossover frequency of a closed loop system that we desire. So I believe this is very similar to what we did for lead compensators, right? So what's shown here in this block diagram is a feedback control system where the plant is G of S and the controller to be designed is our PID controller, C sub PID of S, and the loop transfer function is the product of these two, and that's denoted as L of S. Okay. So what we're trying to design is a PID controller taking this form, the ideal form. So we're going to design the ideal form, and if you really want to realize it physically, then you include you can shift the pole here and include an additional pole at the differentiator. Okay. So that's what happens at the implementation stage. But at the design stage, we just be working with the ideal form of the PID controller. Okay? Now we can do some rearrangement and re-express this equation in terms of this expression here. So this is equal to this, and we're gonna factor out the term Kp over Ti times S from the PID controller and define what remains as C hat sub PID of S. Okay, so C hat sub PID of S is simply equal to the numerator here, which is 1 plus TIS plus TITD S squared. So designing a PID controller is simply about deciding on the values of KP, TI, and TD, because the form of the PID controller has been fixed. So we're basically finding the values of these three parameters. That's what we mean by designing a PID controller. Okay. Now, usually the factor KP over TIS is determined from the steady state requirements, the steady state error. And so we're going to include this term, KP over TIS, in the plant. So we're going to move this term from the PID controller to the plant. And what's left here is then C hat PID of S, which is the numerator of the PID controller. Okay. So easy peasy. So we have moved the term KP over TIS from the original PID controller to the plant. And then what's left is then C hat, PID of S. Okay, any questions? No? Okay. So then we're going to proceed with synthesis. So remember, we assume that we know two things. Or we have decided on the values of two things: the crossover frequency and the phase margin. Okay, so this is given information that we're going to use to design our PID controller. That is finding the values of KP, TI, and TD. So at the crossover frequency omega naught, which is positive, we know that the gain, the loop gain at this frequency is equal to 1. Right? That's the definition of crossover frequency. Okay? And the phase of the open loop transfer function at j omega naught is equal to the phase margin minus pi. Right? That again is simply the definition of the phase margin of a closed loop system. So if you have attended the previous 2 to 3 lectures, this should come to you as your second nature. It should come to you naturally, yeah, right? So based on these two equalities, we can find out what the gain of C hat PID at j omega naught is, and the phase of C hat sub PID at j omega naught is. So what is it? It's simply, so the gain or the absolute value of C hat sub PID at j omega naught is then equal to Ti times omega naught over Kp times the gain of G at j omega naught. Okay? Just based on the first equation here, which is the loop gain at j omega naught being 1. Okay? And from the second equation here, we can determine that the phase of C hat sub PID at j omega naught is equal to the phase margin minus pi over 2 minus the phase of G at j omega naught. So pi over 2 comes from where? It comes from Kp over Ti j omega, right? This term here. So the phase of Kp over Ti j omega naught, that's equal to pi over 2, right? And the phase of this is the phase of the first term plus the phase of the second term. Okay? So any questions? No questions? No? Right, so what we originally had was Pm minus pi, right? So if you take the phase of the open loop transfer function at j omega naught, what you get would be the phase of C hat PID at j omega naught plus the phase of G at j omega naught minus pi over 2. So you move pi over 2 minus pi over 2 plus the phase of G omega naught to the right-hand side, and this is what you get. Okay? The phase margin minus pi over 2 minus the phase of G omega naught. Okay? Any questions? No? Now, we also know that C hat sub PID at J omega naught is equal to this guy here, which is 1 minus omega naught squared Ti times Td plus J omega naught Ti. Well, where does this come from? Well, it comes from simply substituting J omega naught into this expression here, well, into what C hat PID of S is, which is the numerator of this guy. So you substitute S equals to J omega naught into this polynomial, and you get what's shown here. Okay? Any questions? Now we have information about the gain of C hat sub PID at J omega naught and the phase of C hat sub PID at J omega naught. And also we have the form of C hat sub PID at J omega naught. So how do we fix the values, how do we select the values Ti and Td so that this has a gain equal to this and has a phase equal to this? Any idea? 你上次问过这个问题对吧？所以这是由你回答。现在我有 C hat object 吗？现在我有 C hat， 我有这个 expression， 然后我有它的 gain， 我有它的 phase， 我怎么选择 TD 和 TI 来使得我的 gain 在这里是等于这个，然后在 J omega naught 是等于那个 phase？ 我记得你问过这个。So the answer is given on this slide, but how do you obtain these formulas? You're confusing it with finding the maximum phase achievable by a lag or lead compensator. But this is just about choosing the values of Ti and Td so that C hat at J omega naught has a gain that's equal to a number, a given number, and has a phase that's equal to a given number. So how do we select Ti and Td? Well, we can select Ti and Td based on these two formulas, but how do we obtain these two formulas? From the equations on the previous slide. So now we're trying to select the values of Ti and Td so that C hat has a gain equals to this and has a phase equal to this. How do we do that? Why? Why? By setting Ti and Td to be well, according to the formulas on the next slide, will give rise to these two equations here. Why is that the case? Right, anybody else? Can you please help out your fellow student?那我记忆力还不错吧？我记得你 lead compensator 的时候，你就问过类似的问题。现在我说出来，也就是啊，好像是真的是我问的。你想一下，为什么这里会出现 cosine 和 sin？哦，你看有同学帮你答出来了，所以期中考没有作弊。What do we have here? C hat PID J omega naught is equal to 1 minus omega naught square TD plus J omega naught TI. And this is also equal to this is also equal to the absolute value of C hat sub PID at J omega naught times exponential J phase of C hat PID at J omega naught. And this is equal to cosine Now, if you match the real and imaginary parts, 所以记得是你问的吗？是你问的，哦，是你问的，啊，那我记错了，哎，不是你，啊，好，那我不好意思，是你问，是吗？你问的吧？当真是你问的？好，那就你问，应该找你来答。你刚才为什么不答？So any questions on this part? So if you just compare the real and imaginary parts and match the real and imaginary parts on the left and the right, you will obtain the formulas stated on the next slide, on this slide here, okay? Any questions? Well, so we can begin by matching first the imaginary part, and then you get the first equation on the top of this slide, right? So omega naught Ti is equal to the gain times sine phase, right? And that's the first equation on this slide. And then if you match the real parts, you get the second equation on this slide by substituting into it the mathematical expressions that you obtain for the first equation. Okay. Now, some properties that we can note here are C PID of S has a phase between minus 90 degrees and 90 degrees, as we mentioned earlier. That means the phase of C hat PID at j omega naught lies between 0 and pi. Okay? As well, you can immediately see it from here as well. Okay? So the phase of this number would lie between 0 and pi. Because this bit is positive. So the real part could be positive or negative, but the imaginary part is always positive. So the phase of this bit, this guy, lies between 0 and pi, right? You can see it from this equation here. The imaginary part is always positive. 要么第一象限，要么第二象限。So we have this guy here. The phase of C hat PID at j omega naught lies between 0 and pi. What does that mean? It means sine of sine of the angle of C hat PID at j omega naught is positive, which means Ti is greater than 0. And since usually we would assume that Td is always positive, is also positive, so we will have the gain of C hat PID at j omega naught being less than 1 over cosine the phase of C hat PID at j omega naught, when the phase of C hat PID at j omega naught lies between 0 and pi over 2. So that is when cosine is positive. Any questions? No questions? Okay. Questions? No? Questions? No. Okay. So let's now look at a numerical design example. We're going to consider the following open loop plan. G of S equal to 40,000 over S plus 1, S plus 2, S plus 10, and S plus 20. So our goal is to design a PID controller so that the compensated system, the control system, satisfies the following requirements. The first is that the steady state error with respect to a ramp input is 0.6. What is a ramp signal? Yes. So what's a step signal? A step signal is this guy, right? This is a step signal. And the ramp signal is this guy, right? That's a ramp signal. You should have learned about this in signals and systems. That's a ramp signal. So the steady state error with respect to RAM input, reference input, is required to be 0.6. The phase margin is required to be 60 degrees. And the crossover frequency omega naught is supposed to take place at 2 radians per second. So these are the 3 goals that our controller has to satisfy. Our PID controller has to satisfy. Okay. Any question? No? Okay. So based on the steady state error requirement, we can first compute the ratio Kp over Ti. So remember, we said before that the factor Kp over Tis is usually determined from the steady state requirement. So now we're going to determine what the ratio of Kp to Ti is based on the steady state requirement for this example that we're studying. So we're going to first compute the ratio Kp over Ti so that the steady state error requirement is satisfied. To do this, we're going to recall the fact that the steady state error for ramp input is given by the following. Any questions about this? No, right? So the Laplace transform of a step input is 1 over s, and the Laplace transform of a ramp input is 1 over s squared. Right. So in the past few lectures, we have been applying the final value theorem to a step signal, and here we're just applying the final value theorem to a ramp signal. And this is what we get. I hope everybody is happy with that. We have a 1 over s squared here instead of 1 over s, because we're studying a ramp signal instead of a step signal. Okay? So the steady state error for a ramp input can be found as this, and you can substitute whatever you know about CPID and G into the equation, and this is what we get. There's a very silly typo here. Can anybody spot it? There's a very silly typographical error, a typo here. Can you spot it? This is annoying. Why are there so many typos? Yeah, part of it is my mistake as well. So I should have checked it more thoroughly. So typo. I'll fix it and then repost the slides online. But哪里有打字错误? So the limit should be s tends to 0, not s tends to infinity. As t tends to infinity, but s tends to 0 when you apply the final value theorem. And as s tends to 0, what you get is then Ti over 100 over K, Ti over 100 Kp. So that is the steady state error for a ramp input. Now, in order to achieve a steady state error of 60%, that's pretty large, isn't it? But 0.6, we're going to require that Kp over Ti is 1 over 60 or smaller. Or larger, yeah. Yeah. So Kp over Ti, let's set it to be 1 over 60, so that the steady state error is exactly equal to 0.6 for this example, for this design example. Okay, any questions? You don't have questions for me, but I have questions for you now. Why do we, in this lecture, look at steady state error with respect to ramp input instead of a step input? What happens when we look at the steady state error of a step input? For this example. Yeah, what is the steady state error with respect to a step input? What do you think it is? 这里变成 e 除以 s 嘛？那答案是什么？ e 除以 s square 的时候，你 take s 趋近于0，它是一个常数。那 e 除以 s 的，如果这里是 e 除以 s， 0，对啊0啊，怎么可能还有？啊啊！你自己把 e 除以 s 抽出来，它就爆掉了，然后就把那个 s 趋近于0的时候 e 除以 s 不是爆掉了？然后你把它抛掉，你剩下的肯定就是0。不然你自己算也行。So what you will have is then this bit here. But then there's an s in the numerator. So when s tends to 0, it's going to be 0. This is actually something known as internal model principle. So if your controller or your plant has an internal model of a signal that you want to track or disturbance that you want to reject, in this case, it's 1 over s. So you want to track 1 over s, which is a step signal, right? But your controller has a 1 over s inside it. Your controller has a 1 over s in it. So it has an internal model of a signal that you're trying to track or disturbance that you're trying to reject. Then you usually achieve zero steady state. You always achieve zero steady state error. It's known as the internal model principle. It's supposed to be lecture 12. But then because of 2 typhoons that we experienced during the semester, we're not going to cover it. But if you really like to learn about it, we can postpone the exam to week 17 and then cover internal model principle next week. Any? No? No, so you're fine with sticking with the original plan of having the exam next week? Yes, no, yes. Okay. In any case, because we have an internal model principle of 1 over s in our controller, so whatever, if you had a step reference that you're trying to track, the steady state error will always be 0. You can intuitively see it here. If you had a 1 over s factor that you can pull out, and then you multiply the numerator and the denominator by s will appear in the numerator, and as you take s to 0, this will become 0. So the steady state error will be 0. In any case, that's this course. So let's get back to this example. So we're saying that in order to achieve steady state error with respect to RAM input of 0.6, we're going to set the ratio Kp to Ti to be 1 over 60. Okay. Now next, we're going to compute the gain of C hat sub PID and the phase of C hat sub PID at omega naught equals to 2, because the crossover frequency has been specified to be 2, right? So we're going to note that the loop gain must be equal to 1 at omega naught equals to 2. Okay, so at omega equals to omega naught equals to 2, the open loop gain has to be equal to 1. Then we can substitute the expressions for C sub PID and G into this expression here and set it equals to 1 at omega naught equals to 2. Then we can then get the gain of C hat sub PID at J omega naught equals to the absolute value of this guy here, which is approximately equal to 3.8884. Any questions on this? No? I remember there will be one exam question on synthesis, all right? So what I'm covering now is synthesis, a design example, right? Now, secondly, the phase of C hat sub PID at omega naught equals to 2 must be equal to the phase margin minus pi over 2 minus the phase of G of J omega naught, right? As we have seen on previous slide. And hence, by substituting what we know into the equation, we get that the phase of C hat sub PID at J omega naught is approximately equal to 1.666 radians per second. Now with these values, then we can substitute our knowledge, the information about the gain of C hat at J omega naught and the phase of C hat at J omega naught into the long formulas on this slide here and find out what the values of Ti and Td are, right? So Ti and Td are approximately equal to 1.9354 and 0.1769 respectively. Finally, since Kp over Ti is equal to 1 over 60, we will then have Kp is equal to Ti over 60, which is approximately equal to 0.0323. So putting together all we know about the values of Kp, Ti, and Td, our PID controller then takes the above form on top of this slide here. Okay, so we're going to plot the Bode plot of G of S in blue and the Bode plot of G of S times C PID of S in green. So we can see that the blue curves here show the Bode plot of G of S, and that is the uncompensated plan, the plan to be controlled. And the green curves show the compensated plan, or the loop transfer function, G of S times C PID of S. Okay. So now we're going to check whether our design has satisfied the requirements. So what is the crossover frequency for the compensated system? It's located at 2. Here, 0 dB line is here, and it crosses the 0 dB line at exactly omega naught equals to 2, right? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 2 in log scale, okay? What about the phase margin? So at frequency equals to 2, the phase or in degrees is minus 180, sorry, minus 120, and that's exactly 60 degrees away from minus 180. So the phase margin is 60 degrees, which is pi over 3 radians per second, right? So the crossover frequency is supposed to be 2 radians per second, and the phase margin is meant to be pi over 3, or equivalently 60 degrees. So our design controller meets the requirements on the crossover frequency as well as the phase margin. The crossover frequency is 2 radians per second, and the phase margin is 60 degrees, or pi over 3 radians. What about the steady state error with respect to RAM input? Well, let's look at the RAM response of 1 over 1 plus GC. And the maximum value is 0.6. And hence, we are done. We have, this is supposed to be C sub PID, sorry. So 1 over 1 plus G C sub PID of S. Okay. So we have satisfied all three design requirements that we meant to satisfy with our PID controller. Any questions? No questions? Any questions?